In this video, we are going to evaluate Fresnel integral, that is integral from 0 to infinity sine of x squared dx using Laplace transform. Okay. Uh, but we cannot directly take the Laplace transform of this integral. We need to make some changes, such as making I of t equals to integral from 0 to infinity sine of dx square dx. This is because if we do this, now when our integral is in terms of t, we have x squared as constant, and at that time we can evaluate the integral. So for that purpose we have done this. And now we'll try to take Laplace transform of this integral. Yeah. And for those of you who don't know what Laplace transform is, Laplace transform of f of x is just the integral from 0 to infinity. We introduce e to the power minus st over here, and then we have f of let's say if this is t, f of t, so f of t dt. So this is the Laplace transform of e to the power of f of t, and this is mainly used in solving differential equations because it brings all those second derivatives, first derivatives, and just functions, all of these into just functions in terms of simple non-differentiated functions, and then we can use some algebra and solve it, and then take inverse Laplace transform to get the solution. So that is how it helps in solving differential equations. But here we are going to use it to solve this integral. Okay. So now, first of all, we will take the Laplace transform, and then we will make some changes in the order of integrals, due to which we can evaluate in a way that t is our main variable and x square is constant. And then after evaluating these integrals, we will again take the inverse Laplace transform, and then substitute t equals to 1 as our main case over here. So in that way, we can solve this integral. Now let's begin. We are going to take Laplace transform of this integral. Yeah. Laplace transform of I of t is this is I of t. So Laplace transform is 0 to infinity e to the power minus st. So and I of t dt. So this is the Laplace transform. And now integral from 0 to infinity e to the power minus st, and I of t is just 0 to infinity sine of dx square dx, and then dt. Okay, so now since this is in terms of x, this integral is in terms of x, so for this integral e to the power minus t is just a constant. So we can take constant out or take it in, that doesn't matter. Yeah, because this integral in terms of x, this is a constant, and we are going to bring it inside the integral. Okay. And this is integral from 0 to infinity, integral from 0 to infinity e to the power minus st, and then sine of dx square dx dt. Now we are going to perform change of integrals. Since these both the integrals are begin with constant values and end with constant values, and they don't depend upon any variables. If they are dependent on variables, the change of integrals would have been a bit complicated. We need to abide by some other rules, but if they are constant, we can just easily integrate change those limits. Yeah, and this is all supported by Fibonacci theorem. So now we are going to change the integrals, and here we have dt for this first integral now, and dx for second integral now. So this is allowed if the limits of the integrals are constants, and for non-constant we have some other rules. dt dx. Now it makes our work easier since we are dealing with t. The x square will be constant, and we can easily perform this integral now. And you may also notice that this inner integral, uh, yeah. Now you may also notice that this inner integral is just Laplace transform of sorry, it's just Laplace transform of sine of dx square. Yeah, where our uh, t is variable and x square is constant over here. Since this is in terms of t, and this is just the Laplace transform of sine of dx square. As I already mentioned, that Laplace transform of f of t is just integral from 0 to infinity to the power minus st f of t dt. So now we have a standard formula for Laplace transform of sine of at. So Laplace transform of sine of at is just a square by t, sorry, not a square, just a by t square plus a square. So if you want to derive this, it's not that hard though. I can just show you some glimpse of how we can have it. This is just integral from 0 to infinity e to the power minus st sine of at dt. Yeah. And now to evaluate this, what you can do is, this is sine of at is just imaginary part of e to the power iat. Yeah, so you can have that e to the power minus st and then e to the power iat dt. Now you can evaluate this integral. The final result will be a by a square plus t square. Sorry, and it's better if I had written as over here, since after Laplace transform we are in the complex world where the variable is as instead of t. That would be better. That would be better. Instead of saying better, that's recommended. And then this imaginary part of integral from 0 to infinity e to the power t minus s plus ia dt. So now we can evaluate this easily. So integral of this thing is s plus ia by minus s plus ia, and from 0 to infinity, and this is imaginary part of, now at infinity our t is infinite and we have negative sign over here, and note that s would be greater than a in this case, and then negative infinity will be just 0, and after that we have negative sign, and this will be when it's t is 0, 1 by minus s plus ia. Okay, so now this proof is getting longer, and this is imaginary part of 1 by s minus ia, and now we would just rationalize this to get s plus ia by s square plus a square, and so now we see that the imaginary part of this thing is just a by s square plus a square. Okay, so you have got the why this is a by s square plus a square. So now after you have this, I'm going to erase all this. Okay, so now we know that Laplace transform of sine of at is a by s square plus a square. We'll use that over here, integral from 0 to infinity. This is a sorry, and our constant is x square, so x square by s square plus x to the power 4 dx. Now to evaluate this, first of all, what we can do is we can take the constant term out. We can take the constant term out. This will be 1 by s square, and then 0 to infinity x square by 1 plus x over root s to the power 4, and then dx. Now what we can do is we can just let y as x to the power x by root s. Okay, and that will give us dy root s as dx. Note that we are trying to change it to the form where we can use beta gamma functions. Yeah, yeah, you will see in a moment how the beta gamma function comes here in this integral from 0 to infinity. We have 1 plus y to the power 4 over here. Yeah, and then we have over here x is just root sy, so that's s times y square. Okay, and over here dy root s, so that's give us 1 by root s integral from 0 to infinity y square by 1 plus y to the power 4. Now we have our final step where we can now finally change it to standard form of beta gamma function. Now we need to let z equals to y to the power 4. Yeah, and then we have z to the power 1 by 4 equals to y, and 1 by 4, sorry, I'm extremely sorry for this. This happens most of the time. Okay. But the good thing is it's saved automatically. Yeah, now for this one, now we can let z equals to y to the power 4, and then z to the power 1 by 4 equals to y, and 1 by 4 z to the power minus 3 by 4 dz equals to dy. So now we can use that, and we have integral from 0 to infinity. Y is just z to the power 1 by 4, so that is z to the power 1 by 2 over 1 plus z, and dy is just 1 by 4 z to the power minus 3 by 4 dz. So now it's almost in the form where you can use beta gamma functions. It's 1 by root s times 1 by 4 integral from 0 to infinity. This is z to the power minus 1 by 4 and 1 plus z. Yeah, this is then 1 plus z. Okay, and then dz. Now we know that beta of m and n is integral from 0 to infinity x to the power m minus 1, sorry, beta of m comma n is integral from 0 to infinity x to the power m minus 1 by 1 plus x to the power n plus 1. So you know that beta of m and n is just this function. Now we'll try to change it to this exact similar form, 1 by root s 1 by 4, and this will be integral from 0 to infinity z to the power 3 by 4 minus 1 by 1 plus z to the power 3 by 4 plus 1 by 4. This 1 by 4 is because we have to make here 1 in overall. Now it's in the form where you can use beta gamma functions, and this is 1 by root s 1 by 4, and this is just beta of 3 by 4 comma 1 by 4. Now to evaluate this, okay, we need to know that beta of m comma n is just gamma m gamma n by gamma m plus n, and this gamma of m is just m minus 1 factorial, and for fractions we need to evaluate it by some special means. And also you need to know that gamma of m and gamma, sorry, is it working? I'm extremely sorry, it's not responding. Let's just wait for a few seconds. Yeah, after this what we will do is we will try to evaluate this beta function of 3 by 4 and 1 by 4. Okay, so that will be gamma 3 by 4 gamma 1 by 4 over gamma of 3 by 4 plus 1 by 4, and gamma of 3 by 4 plus 1 by 4 is just gamma 1, that's 0 factorial, so that's 1. And in the numerator, for evaluating gamma 3 by 4 times gamma 1 by 4, what we can do is we notice that it's just gamma 1 by 4 times gamma of 1 minus 1 by 4. Yeah, and now we have a function of we have property from gamma function that gamma of m times gamma of 1 minus m is equals to pi by sine of n times uh, yeah now I can write. So we have provided from gamma function that gamma of m times gamma of 1 minus m is just pi by sine m pi. So we have this property from gamma function and we will use this here. So it's 1 by root s 1 by 4 times gamma 3 by 4 gamma 1 by 4 over gamma 1 over gamma 1. So that's 1 by root s times 1 by 4 times this will be pi over sine of 1 by 4 times pi, and over gamma 1 is just 1 since that's just 0 factorial, and now we get it to be 1 by root s and then 1 by 4, and this will be pi by 1 by root 2. So that's 1 by root s into 1. This is pi, sorry, so this is pi by 1 by root 2, so that will be pi by 2 root 2 now. So now I finally evaluated the Laplace transform over here. So now we have Laplace of I of t as for all this evaluation, and now we can write here Laplace of I of t. And note that we couldn't directly evaluate the integral I of t, but the integral that we got from Laplace of I of t, this was solvable. The Laplace transform was solvable, though it is all solvable from some standard means, but naturally we couldn't do that, so we used Laplace transform, and now this was solvable. Okay, now we are going to use inverse Laplace transform to go to again the original world from the Laplace world. Okay, now we will use inverse Laplace transform, and note that since Laplace is linear, we can take the constants out, and 1 by root s, we need to perform some things. Yeah, now this is I by t and pi by 2 root 2 in Laplace transform of 1 by root s. Okay, and now to find the inverse Laplace transform of 1 by root s, okay, you need to note this thing. Okay, now Laplace transform of t to the power minus 1 by 2, so it will be from integral from 0 to infinity e to the power minus st, and then t to the power minus 1 by 2 dt. Yeah, and now this integral, we know it's just okay, for this also you need to know Laplace transform, or you can just substitute st as some function u, and then here u to the power minus 1 by 2 by s to the power minus 1 by 2. You can do by that substitution, substitute that u equals to st, and then you can use the property of gamma function, and after that you will get this integral to be gamma of 1 by 2 by s to the power 1 by 2. So now if it's somewhat similar in this form, so we know that Laplace transform of t to the power minus 1 by 2 is gamma of 1 by 2 by s to the power 1 by root 2. Now you can take this gamma 1 by 2 to other sides, and since Laplace is linear, we can bring it to denominator. Okay, so that's 1 by 2, and over here it's just 1 by s to the power 1 by 2. Now you can see that the inverse Laplace transform for this integral t to the power minus 1 by 2 by 1 by 2 is the inverse Laplace transform for this 1 by s to the power 1 by 2. So now this inverse Laplace transform is just pi by 2 root 2, and then t to the power minus 1 by 2 by sorry, this is gamma of 1 by 2, not just 1 by 2, gamma of 1 by 2 by gamma of 1 by 2. Okay, now let me erase all the things over here. It's really pretty long. Since I've tried to grab all the expressions, the video got a bit long. Now, this thing is pi, gamma of 1 by 2 is just root pi, so we get root pi over 2 root 2 times 1 by root t. So that's the integral I of t. So this is just I of t, which was integral from 0 to infinity sine of tx square dt. So this integral is root pi by 2 root 2 times 1 by root 2. Now you can substitute t equals to 1 over here to get our required Fresnel integral. So it's integral from 0 to infinity sine of x square dt is just root pi by 2 root 2. So that's the answer. I hope you enjoyed this video where we solved this integral using Laplace transform. And thanks for watching. If you have any doubt, do comment in the comment section below. I'll try to solve it. Thank you.